Now, as we get into the genetics, and we've described before in some of the previous objectives, we talked about what are genes. We talked about a little bit of introduction of alleles, and we're going to describe that a little bit more. We're going to talk about dominant versus recessive. We'll talk about carriers. We'll talk about probabilities and doing some of those. And what's great about this stuff is it gives us predictability on certain disorders. Now, what we have to understand is that there are certain disorders that we deal with, and it's the smallest number, but these are what we refer to as single gene disorders, that there is one problem. I mean, how many of you potentially, now most of us live in a house where there's probably a couple things that bug us, but let's say that you live in a house and there is just one thing that drives you crazy. That, okay, this wall it's in a stupid spot, or this door is too short, or this is too, okay, you just got one single problem, okay, and sometimes that can be bad. In other words, it can be something that just makes it non-usable. And then other times it's like, yeah, it bugs me, but it's okay. Well, genetic diseases work the same way. There are some diseases that are far more debilitating than others. Okay? Well, what it relates to is the instruction manual. So we said that a segment of DNA along a chromosome that codes for specific protein products and traits is a gene. And we all have essentially the same genes. We have hair-colored genes, we have collagen genes, we have elastin genes, we have all sorts of genes that give us structure and give us function. And these genes, we make them, but sometimes, well, what if the instructions aren't correct? Okay? Now, I think this is one example that seems to work. Students appreciate it. If you think about, okay, let's say you're at a party, and somebody says, hey, we need ice cream. Who doesn't like ice cream? Everybody loves ice cream. And so the question comes up, well, what kind of ice cream do you want? And let's say that you're told to go on the ice cream run. They say, okay, here's some money, go buy vanilla ice cream. So you end up going to the store, you stand in front of the freezer case, you open up the door, and you stand there and you kind of just take a big deep sigh, like, ugh, because what? There's like 20 different kinds of vanilla. So they told you to buy vanilla, but now what kind does everybody want? Do they want the really, really cheap vanilla? Do they want the way expensive vanilla? Do they want French vanilla? Do they want double vanilla bean? Do they want, I don't even know all the flavors because I don't do vanilla. Why do vanilla when you have chocolate? But you have all these options of vanilla. Okay, you got all the vanilla flavors. Well, what do? So the relationship I want to bring out of that is you have a particular gene. And earlier I used the example of your ABO blood type. You have your blood type gene that gives you your ABO blood type. And on chromosome 9, where this thing is located, well, you happen to have 2 chromosome 9s. You got one from mom, you got one from dad. And one of them has a version of that gene, and another one has a version of that gene. Both of them have a blood type gene there, but they may not be the same version of that gene. Just like there's vanilla, but there are different kinds of vanilla. So when we talk about the gene, we're talking about what is it coding for. When we talk about the version of that gene, the term for that you want to understand, the term is the allele. So an allele is a variation in a gene. So you have the A allele of the ABO blood type gene. You have the B allele of the ABO blood type gene. You have the O allele of the ABO blood type gene. And so you're going to get 2 of these. One from mom, chromosome number 9. One from dad, chromosome number 9. And it's the combination that determines what you express. Okay, now we don't test you on this term in this unit, but if you ever hear the term genotype, genotype is what you are. Are you AA? Are you AO? Are you BO? Are you BB? Are you OO? Are you AB? Those are your options. Okay, that's your genotype. Your phenotype is what you express. When I blood type you, when we blood type you, and we'll do that next in the 1111 class, are you A, are you B, are you O, are you AB? So what you can be genetically, you have a little bit more, greater number of combinations than what you would test for. And that's genotype versus phenotype. Now, the reason that happens is, well, let's look at those options and say, all right, someone can be AA, someone can be AO, someone can be BB, someone can be BO, someone can be OO, someone can be AB. Those are the options. Remembering that you inherit one allele from each parent. So this would be, dad gave you an A, mom gave you an A. One parent gave you an A, the other gave you an O. B, B, so on and so forth. Okay. Well, what happens in this scenario, okay, is the fact that now what you want to remember here, and we mentioned it on the slide, what you want to remember here is, well, Dad has 2 chromosome 9s, but he's only going to give you one of them. So you have a 50-50 chance of which one you're going to get. Okay, Mom has 2 chromosome 9s. So you got a 50-50 chance of what you're going to get. So let's say that with this, these are your options. Okay? But let's say that these are, now if we really wanted to get all of these options, okay, we could have a situation where Dad, okay, well actually let's do Mom, okay, because we're going to make a joke about it. Okay, let's say that Mom has an A allele and an O allele. Those are her genetics. That's her genotype. Dad, because Dad stinks, he's BO. Okay, so Mom is AO, Dad is BO. Could I not get an A? Oh, I couldn't get all of these. Doesn't work. Okay, go with me here. So I could get an AB, I could get an AO, I could get a BO, and I could get an OO. So those are the combinations I could get, okay, out of that. And we're going to describe how we can kind of predict that if that's what Mom and Dad are. So I couldn't get this. Well, why? Well, I could get the A from Mom, but Dad doesn't have an A to give. So he can't give it to me. So I can't have that blood type. If this is the, now in genetics we don't call it Mom and Dad, we call it the mating pair. Okay, Mom and Dad status, marital status not required. The mating pair, okay, is what it's referred to as. So I couldn't get this from that mating pair. Could I get an AO? Yep, A from Mom, O from Dad. Could I get a BB? I could not, because Mom doesn't have a B. Dad does, Mom doesn't. So we couldn't get that. Could I get a B and an O? I could. Could I get an O and an O? I could. Could I get an A and a B? I could. So I have 4 options of the offspring of that mating pair. So can a mom who's A have an AB child? Yeah. Can a mom who's A and a dad who's B have an O child? Because that seems kind of weird. They can. Now, sometimes these alleles, we refer to them as being dominant, or we refer to them as being recessive. A dominant allele is one where if you inherit it, you express it. A recessive allele is one that is only expressed in the absence of a dominant. Let me repeat that. A recessive allele is one that will only be expressed in the absence of a dominant. Okay, now let's show an example of that. So in the case of A, B, and O, it just so happens A and B alleles are dominant. What does that mean to me? That means if I get them, I express them. That's the word I was looking for. O alleles are recessive. So I will only express them in the absence of a dominant. So with an AO, A is dominant, O is recessive, so which one am I going to see? I'm going to see the A. So that person's blood type is A. With a BO, the B is dominant, the O is recessive. Dominant will be expressed, therefore what's their blood type? Okay, their blood type is B. So I can have a person who's BB and I can have a person who's BO. Both will have the B blood type, just for a different reason. Now, OO. O is recessive. O will be expressed in the absence of a dominant. There's not an A there. There's not a B there. Therefore, that person, okay, would be blood typed as O, because there's not an A, there's not a B. AB, those can be codominant. So if you get an A, it'll be expressed. If you get a B, it'll be expressed as well. Okay? So that's where that situation comes in. Dominant alleles versus recessive alleles. So the way we describe or show or try to predict probability is we use what are called Punnett squares. And the Punnett squares are going to, now these are single genes. Okay, I'm only dealing with one gene. And what we do with these Punnett squares is we show what are mom's alleles and what are dad's alleles. Now it's easy because these are round, therefore they look kind of like eggs, and these obviously have tails, so these are sperm. So this is mom and this is dad. So in the process of meiosis, we split their chromosomes and we can get different combinations. Now the way we list this, and they're using the letter P, and in this scenario we list the dominant gene with a capital letter. We list the recessive gene with a lowercase. Now what you want to keep in mind here is dominant doesn't always mean good and recessive doesn't always mean bad. Now, by and large, most of the genetic diseases we deal with, single gene disorders, the genes causing the disease are recessive. So they would be indicated with the lowercase. But there are some genetic diseases where they are dominant. Okay, recently, with the NBA draft, there was the big, tall kid from Baylor University that they honored at the NBA draft because he was due to be drafted. I think they were talking about him being drafted. Obviously, when you're 7'1", kind of increases the likelihood you're going to make a lot of money playing basketball. But he was expected to be drafted somewhere around pick number 13, pick number 14, somewhere in that range. And so they stopped and honored him because he had to withdraw his name from the NBA draft for medical reasons. That medical reason being a condition called Marfan syndrome. And in Marfan syndrome, it is a dominant, it's an autosomal, somewhere on pairs 21 through 22, autosomal dominant disease, where if he got a bad gene from one of his parents, he would have the disease similar to them. And they did the genetic testing, is my understanding, and found out he has the bad gene. So it puts him at risk. And what happens in Marfan syndrome is it's a defect in forming the elastic fibers of your connective tissue. And so your connective tissue lacks the elasticity, especially the aorta. When we think about the pressure in the aorta, and most often individuals, when they die of Marfan syndrome, is because they have a ruptured aorta, or they have an aortic aneurysm that ruptures, and that leads to them bleeding to death internally, and that becomes their cause of death. So anything that would increase blood pressure dramatically and increase the workload of the heart can push on that defect and likely rupture that aneurysm. So that's why he chose to withdraw from playing basketball, still involved in basketball, but playing. But that is a dominant disease. So we would make that a capital letter. So do keep that in mind. You need to know what your disease is. By looking at this, we've determined that mom is big P, little p, dad, big P, little p. And let's say in this scenario that the disease, let's say this is representing a disease, and the disease is recessive. That means the gene that causes it, the allele that causes it, better said, the allele that causes it is recessive. Therefore, wherever there's a little p, okay, that's representing that diseased allele. But being recessive, it's only manifest in the absence of a dominant. Now, what this is representing is a disease called PKU. Now, remember, most of you have heard of this. PKU stands for phenylketonuria, and it's a condition where an infant, well, a person, doesn't metabolize the amino acid phenylalanine correctly. And due to its problem with its metabolism, it causes severe mental retardation. And it's something we want to catch early because it's treatable. It's treatable that you just don't consume many foods that have phenylalanine in it. But it is recessive. So being recessive, to manifest a recessive allele, it only is manifest in the absence of a dominant. Okay, so take that statement. Okay, take that statement. The disease will only be expressed in the absence of a dominant, and say, okay, from this mating pair, dad over here, big P, little p, mom over here, big P, little p, here are the combinations. Big P, big P, big P, little p, big P, little p, little p, little p. Those are the options. So which one would actually manifest the disease? Okay, the disease, recessive disease, will only be manifest in the absence of a dominant. Well, there's only one option here where it's missing the dominant, and that's the bottom right, little p, little p. So this would be an affected child. This would be an unaffected child. Doesn't even have the recessive allele, so it doesn't matter. These two are what we call carriers, because do they carry the recessive allele? They do. So therefore, can they pass it just like their parents did? Yes. But because they have the dominant healthy gene, they can metabolize PKU or phenylalanine just fine. It's one of the 20 amino acids. They can metabolize it just fine. Therefore, they are carriers. So we could call these, we can get my arrow back, we can get these as healthy non-carriers, healthy but carriers, and diseased. And when we find somebody with PKU, this is what we see. Now, similarly, we can look at individuals who would suffer from lack of melanin pigment. Doesn't mean they lack melanocytes. It just means they lack production of melanin, albinos. It's also autosomal recessive. So in that situation, we're saying that dad, big A, little a, so he's a carrier. Mom, big A, little a, she's a carrier. So they can have a healthy non-carrier, okay, 50% of the time, because this is probability. So out of 4, 1 out of 4, do the math, 25%. 2 out of 4, do the math, 50%. 1 out of 4, do the math, 25%. So there's a 25% chance. Now, do keep in mind that the percentages may not be perfect. But let's say that this is a mating pair for this condition. It doesn't mean that 25% of their children are going to be albinos. It just means there's a 25% probability. Because it's like, and this is how Vegas makes money, okay, and Wendover makes money, but gambling institutions make money, is they make you think you know what you're doing. In other words, if somebody plays roulette and half of the spaces are red and half the spaces are black, that means each time that wheel spins, it's got a 50% chance of red and a 50% chance of black. And that never changes, 50-50 every time. So the problem they sucker people in with is they display the numbers and the colors. And they say, hey, look, red has come up 7 times. So there's 2 different ways people think about it. They think about it in terms of, ooh, it loves red today, so I'm going to bet on red. Or they're saying, red's come up 7 times, but it can't come up 8. It's got to be black. So the different ways they think about it, but they think about it wrong from the standpoint of it's always 50-50. So if this is the scenario, there's a 25% chance of having a child with albinism. There's 25% chance of having a healthy non-carrier, and there's a 50% chance of having a carrier. Okay? Sickle cell does that to some degree, but remember we said like with the A and B alleles of the blood type, there can be codominance. In the situation of sickle cell, causing sickle cell anemia, we can have some of that codominance where the typical form of hemoglobin, adult hemoglobin, we call hemoglobin A, that which has a defect, and it's a single, it's a single nucleotide that gets substituted, and we used that example when we talked about the primary structure of protein where we end up with a point mutation. We get a single substitution, and we end up with hemoglobin S. So the combination, let's say I had mom who had a hemoglobin A allele and hemoglobin S allele, dad with a hemoglobin A and a hemoglobin S. The combinations can give normal hemoglobin A. It can give what we call sickle cell trait, where some of the hemoglobin is defective because there's some codominance here, versus that person who would actually suffer the severest form of the disease, which would be one who has both. Okay, so you can see that type of inheritance taking place. So terms you want to understand dominant, you want to understand recessive. You want to understand carriers, you want to understand genes, okay, and that helps kind of put these pieces together. So the question comes up, well, would you like to know your genome? Would you like to know your genetics? Okay, and there's different ways to think about it. Would you like to know your genetic sequencing so that you know, ooh, I have that gene, ooh. Some people might, kind of as a life preparation thing, I don't know. Where others are like, I already lose sleep for a lot of other things. I don't want to lay awake thinking, oh, is that the problem? Is it time now? I mean, it would be kind of horrible. And we don't necessarily want other people to know our information either. How would you like life insurance companies to know, oh, they've got that gene. Ooh, that's bad. That means that we're going to make them pay more because they're going to die when they're 55 or somewhere around there. I mean, there's just all those types of issues. Okay, now most of our disorders that are genetic are what we call polygenic disorders. In other words, heart disease isn't one gene. Okay? Diabetes type 1, diabetes type 2, it's not one gene. There are not only genes involved, but there's also environment involved. So it gets kind of complex. We're making it very simple here with what we refer to as single gene disorders. Okay? But there's a whole lot that goes on, but it's kind of interesting to talk about. So makes it kind of fun.